In this video, we are going to talk about solving first-order linear differential equations. We'll do this using direct integration and also a method called integrating factors. So first we'll define what it is to be a differential equation, and then we'll look at what it is to be a first-order linear equation. We will do our solutions based on two methods of direct integration as well as Leibniz's method of integrating factors. I should also mention I do have this formula here for your reference, integration by parts. It'll come in handy quite often, not just in this video, but in the future as well. We will start with definitions. A differential equation is a relationship between a function of time and its derivative. So for example, it'll have the form dy dt is some function of y and time. So any differentiable function y is equal to phi of t that satisfies this equation for all values of t is considered a solution of this equation. So what does it mean to be linear first order? Well, let's start with first order. So an equation is first order when the highest derivative is of first order. In other words, all we have are dy dt. We don't have anything with a second order derivative like dy dt squared. So those are not in first order differential equations. And what does it mean to be linear? That means our variable y appears by itself. In other words, you don't have y raised to a power like y to the third or e to the minus y or sine of y. It's just y. And then importantly, the form of a linear first order differential equation is dy dt plus p of t, which is a function of t, times y of t is equal to g of t. So one thing that's important to remember here, I have y, and it's understood that y is a function of t. So I have, again, dy dt plus some function of p of t, and then y of t is equal to g of t. This is the form of a linear first-order differential equation, which we will be solving in this video. Our first example is to solve the differential equation 4 plus t squared dy dt plus 2y times y is equal to 4t. I often like to rewrite my y as y of t just to remind myself that it is a function of t, especially once I start to integrate. But I'm going to look back here and look and verify that this is of this form, that it's a linear first order equation. Well, first, it is first order because you only have dy dt. You don't have any second or third derivatives. So the first order derivatives are the highest order derivatives. And then also, if I look at my values for y, I only have y of t here. I don't have any y squared. I don't have signs of y or anything else like that. And looking, if I should be able to put it in this form. So I have dy dt here. Here I don't have anything in front of dy dt, so I can simply divide my whole equation by 4 plus t squared. And you can see now that my equation is in this form of dy dt times some function of t, and it's only a function of t. There's no y's in this function, just a function of t times y of t, which is right here, equals, and then another function of t, no y's, just a function of t, is equal to g of t. So I've put this in this form just to demonstrate for you that I do have a first-order linear differential equation, but for this problem it's not necessary because when we do direct integration, we don't necessarily have to have it exactly in this form, but we can put it, we just have to be able to put it in the form. But basically we want to gather all the y terms on one side. And you can see here I have all the y terms, the dy dt as well as the y of t, all on the left-hand side of the equation. So the right-hand side of the equation only have terms of t, terms with t. My next step is to integrate. So I'm going to integrate with respect to t. So I have the integral of 4 plus t squared dy dt plus 2y y of t, all of this integrated with respect to t, and then on this side I have the integral of 4t dt. And when I integrate, I find that this is equal to 4 plus t squared y of t. And just to verify that is the case, remember I have to use the product rule. If I take the derivative of 4 plus t squared y of t, I've done that over here in blue. Using the product rule, first I take this first factor, 4 plus t squared, times the derivative of the second factor, which is the derivative of y, or dy dt, plus the derivative of the first factor, which is 2t, times y of t, and that's exactly what I have here. So this integrates directly into 4 plus t squared y of t, And this side, I simply have 2t squared plus c. So now to get y of t, I divide my entire equation by 4 plus t squared, and this is my solution. When possible, it's always preferable just to do this direct integration, again, gathering all your y terms to one side and then integrating both sides of the equation. But sometimes it doesn't quite work out. And for linear first-order equations, remember linear means the variable y appears by itself, first order, only dy dt. For equations of this form now, dy dt plus p of t y of t equals g of t, in general, if you can't integrate nicely this first side here, the side with the y terms, then we can see if maybe we can slip in an extra integrating factor, which we'll call mu of t. And that integrating factor, we're going to see if we can multiply this entire equation with this integrating factor and see if we can get this side of the equation integrable. Looking at the last example we just did with direct integration as a guide. So again, if the idea is when we integrate this side of the equation with the dy dt and the y's, but we can't, in this case it was easy to integrate. We used the product rule and we could integrate. But if we can't, what Leibniz realized is if we multiply the whole side of this equation by a proper integrating factor, we could still then use the product rule and figure out that this integral will become mu of t times y of t. So let's look at that on the next slide. And what we will do is do an example so that we have a real example to work with and try to figure out from the example what this mu, this integrating factor, should be. Once we have the example, we're going to kind of follow the same steps to look at, in general, how we can solve these first-order linear equations using an integrating factor. And then afterwards, we'll do a few more examples. For our first example of the method of integrating factors, we're going to look at this problem of find the general solution of dy dt plus 1/2 y equals 1/2 e to the t over 3. If I look at this and try to use my direct integration method, I have here I do have all my y's on one side of the equation, and here I have my functions with only t. So I can try to integrate both sides of the equation, but you can see this is not easily integrable. So what Leibniz would say is we're going to try to find an integrating factor to make this work out. And then to finish this problem, we're going to draw some representative integral curves. That is, we're going to plot solutions corresponding to values of c, because when we integrate, we're going to get this constant of integration. And then we're going to find the particular solution whose graph contains 0, 1. So we'll solve for c when we're at 0, 1. And the idea, again, is we're going to multiply our first-order linear equation by an integrating factor, mu of t. So I'm going to multiply my equation, my dy dt plus 1/2 y equals 1/2 e to the t over 3 by mu of t. So I'll get mu of t dy dt plus 1/2 mu of t y of t equals 1/2 mu of t e to the t over 3. And by the way, it is true, I have the formula for mu of t, but we're pretending like we don't know this. And so we're trying to figure out how do we find a mu of t, and then later we'll derive this formula here. And what I'm going to try is to choose my mu of t such that this part of my equation, my mu of t dy dt plus 1/2 mu of t y of t, is the derivative of mu of t y of t. Another way of saying that is I want to choose my mu of t such that the derivative of mu of t times y of t, which is here, the derivative ddt of mu of t y of t, by the chain rule is mu of t times the derivative of y of t with respect to t, that's dy dt, plus y of t, which is over here, times the derivative of mu of t with respect to t, d mu of t over dt. And I do that so when I integrate both sides of the equation, when I integrate this left-hand side of the equation, mu of t y of t will simply fall out. But now I have to look at this. So if I want my mu of t dy dt plus 1/2 mu of t y of t to be equal to mu of t dy dt plus d mu of t dt times y of t, what that means is this blue part here has to equal this blue part, And this green part has to equal this green part. So take another look. So I have my original equation multiplied by mu of t, and I'm choosing my mu of t such that d dt mu of t y of t is equal to this function here. So what I really want, the blue parts are equal, is I want the green parts to be equal. In other words, I want 1/2 mu of t y of t to equal to d mu of t dt times y of t, which is the same thing as having 1/2 mu of t equal to d mu of t dt, and the y's cancel out. I rewrote this line over here. I just kind of switched the order. D mu dt is equal to 1/2 mu of t. So now if I move this over, what I have is 1 over mu of t. So I divide both sides of the equation by mu of t times d mu dt is equal to 1/2. So now what you see is I have d mu of t over u of t, which is the same thing as the derivative of natural log of mu of t, and that's equal to 1/2. So when I integrate both sides of the equation, what I get is the natural log of mu of t is equal to 1/2 t plus c, which means that mu of t is equal to c times e to the t over 2. And this is my integrating factor. So I haven't solved the equation yet. All I've done so far is find the integrating factor. And just to repeat, we chose our mu of t so that the derivative of mu of t y of t is equal to mu of t dy dt plus 1/2 mu of t y of t, which is exactly what we have here is our original equation multiplied by mu of t. So we're going to take you'll see that as the example progresses on the next slide. Here I kind of summarize this out. We chose mu of t such that d dt mu of t y of t is equal to mu of t dy dt plus d mu dt y of t, and mu of t is equal to c e to the t over 2. And we can choose c equal to 1 to get mu of t equal to e t over 2. You can choose c equals 2 if you want, but why would you make it more complicated? So just choose c equals 1. And now I can multiply my entire equation, my original differential equation, by my e t over 2. So I'm going to have e t over 2 dy dt plus, here I have 1/2 e to the t over 2 y of t is equal to 1/2 e and then e to the t over 3 times e to the t over 2, which is e to the 5t over 6. And so now I can integrate both sides of this equation, and I get the integral of e to the t over 2 dy dt plus 1/2 e to the t over 2 y of t, integrating with respect to t, is equal to e to the 5t over 6, integrating with respect to t. And now again, what we want to remember is mu of t was chosen such that derivative dt of mu of t y of t is equal to mu of t dy dt plus d mu dt y of t. So here I have my mu of t y of t here. So this here, when we integrate it, falls out to be our integrating factor times y of t. And then we can verify, just looking at this, if we take the derivative of this, our e of t y of t, well, by the product rule, that's going to be equal to e to the t over 2 times the derivative of y of t, which is right here, plus y of t times the derivative of e to the t over 2. And the derivative of e to the t over 2 is 1/2 e to the t over 2, which is right here. Okay? So again, mu was chosen so that this would fall out, the integral would fall out to be mu times y of t. And that's equal to integrating this side, 3/5 e to the 5t over 6 plus c, dividing both sides by e to the t over 2. Our general solution is y of t is equal to 3/5 e to the t over 3 plus c e to the minus t over 2. So I rewrote my solution here, our general solution, and now we want to find the solution that passes through 0, 1, kind of like an initial value condition. So when t is equal to 0 and y is equal to 1. So if I set y equal to 1 here, t equal to 0 here, I'm going to get 1 is equal to 3/5 plus c. In other words, c is equal to 2/5. So at 0, 1, our initial value solution is y is equal to 3/5 e to the t over 3 plus 2/5 e to the minus t over 2. And here I went ahead and did the graphs because it asked for solutions of corresponding values of c, and as you can probably guess, I did not draw this figure. Before we go on to how we can generally find a formula for mu of t, I do want to illustrate kind of the steps of this method and do one more example. So for the method of integrating factors, first you want to put it in the form so that the functions of y are gathered on one side of the equation, which is actually very much the same thing you did when you were solving by direct integration. The next step is to integrate both sides of the equation with respect to t. And what we want to keep in mind is that the integrating factor mu of t was chosen so that d dt mu of t times y of t is, by the product rule, equal to mu prime of t y of t plus mu of t y prime of t. And we'll see basically how that makes this integral fall out. And then we have one other point here. If g of t is a more complicated function, it might be necessary to leave the solution in integral form, and we'll have an example of that towards the very end. And the example we're going to use to illustrate this is to find the solution to dy dt minus 2y is equal to 4 minus t. And we're going to plot the graph of several solutions and discuss the behavior as t approaches infinity. Step 1 has already been done for us. All our y terms are on one side of the equation. So on the other side of the equation, we only have the terms that involve t, or a constant. So here is our side with y terms. And then the next thing we should do is multiply by the integrating factor. So we need to find the integrating factor. And in this case, I am going to use the formula. Mu of t is equal to the exponent raised to p of t, in this case, is minus 2. So minus 2 dt. Remember, our p of t is whatever multiplies y. And that's just equal to our exponent of minus 2t, which is e to the minus 2t. So this is our integrating factor. Again, I haven't solved in general. I haven't shown you how we can derive this, but we will derive it next, after this example. Now that we have our mu, we're going to multiply our entire equation by mu. So we have e to the minus 2t times dy to the t minus 2 times e to the minus 2t y of t. And again, I wanted to emphasize that this y is a function of t, is equal to 4 times e to the minus 2t minus t e to the minus 2t. Next, we can integrate both sides of the equation, keeping in mind the integrating factor was chosen because of this product rule that the derivative of mu of t times y of t is equal to mu prime of t y of t plus mu of t y prime of t. So integrating both sides of the equation with respect to t, keeping in mind y of t is y is a function of t, and also keeping in mind this part here is just, when you integrate it, you're just going to be left with mu of t times y of t. And we can verify that. We can just look. If we take the derivative of e to the minus 2t times y of t by the product rule, we're going to get e to the minus 2t times dy dt, which is here. So we did this times the derivative of this, plus this times the derivative of that. So we have our y of t, and our derivative here would be minus 2 in front, e to the minus 2t. So you can see how this worked out. And again, this is the key. When we integrate both sides, we have to realize that we chose our mu of t so that this, when you integrate, will just simply be mu of t times y of t. But now we need to integrate this side of the equation. This part is easy. It's minus 2 e to the minus 2t. And here, when we have t e to the minus 2t, we're going to do that integration by parts. And on the first slide, I had given you that formula. You know, every now and then in this book, you'll need integration by parts, so it's good to remember. Here, I have my formula for integration by parts. So the integral of u v prime dx is equal to uv minus integral of v u prime dx. So I choose u to equal to the minus t. I'm going to choose my v prime equal to e to the minus 2t. So now u prime is going to equal to minus 1, and v is equal to minus 1/2 e to the minus 2t. plugging into the formula, then I have uv, which is minus t, that's u, and v is minus 1/2 e to the minus 2t, minus the integral of v, which is minus 1/2 e to the minus 2t, times u prime, which is minus 1/2. So here, this part here, I'm going to get my minus 1/2 minus t e to the minus 2t, and then the next part here, I get my, actually this should be a plus. When I integrate this part here, I get 1/4 e to the minus 2t. So here, I've done my integration by parts, and I have my 1/2 t e to the minus 2t plus 1/4 e to the minus 2t plus c. And now to solve for y, I'm going to divide both sides of the equation by e to the minus 2t. I'm also going to combine these two terms since they have the same e to the exponent, and I get y is equal to minus 7/4 plus 1/2 t plus c e to the 2t. I have my graph here, which again was not drawn by me, but if I look at this, as t approaches infinity, and I can see this here, if c is less than 0, so this t grows linearly, this grows exponentially, so if c is less than 0, then the solution is going to grow exponentially negative. So these are these solutions. As if c is greater than 0, then solutions will grow exponentially positive. Why did I do this? Just as a note, at c equals 0 and t equals 0, y equals 7/4 is the y value where solutions diverge negatively on one side and positively on the other. Also plugging in c equals 0, you get y is equal to 7/4 plus 1/2 t, which you can see that means y is growing linearly. And that's this line here, which is linear. So now I have shown you in general how you solve these methods of integrating factors. You use this mu of t. I haven't shown you an example of number 4, but I will by the end of the video. And I haven't shown you how we got this formula for mu of t, which is what we are going to do next. Now we are going to look at this general form of our first order linear differential equation, dy dt plus a function p of t times y of t is equal to a function g of t. And we want to be able to figure out, we want to derive what our mu of t is supposed to look like, and it's going to be equal to exp integral p of t dt. And so here, once we have our general form of the differential equation, we multiply by mu of t. So here we have mu of t dy dt, our mu of t p of t y of t, and our mu of t g of t. And I want to remind you that before we considered, after we integrate both sides of the equation, this and this, we wanted our derivative of mu of t y of t using the chain rule will equal to u of t dy dt plus du of t dt times y of t. We want this to equal to this function here, which is our mu of t dy dt plus p of t u of t y of t. And if these two are equal, what that means is since these two are equal, the mu of t dy dt are common here, what that leaves us is that du dt y of t is equal to p of t u of t y of t. And then eliminating the y of t on both sides of the equation, we get this point here, that we want du dt equal to p of t mu of t. So here is our goal. So we can assume mu of t is positive. Then from this equation, we have that p of t is equal to dividing both sides by mu of t, 1 over mu of t du of t dt. And then if we integrate p of t dt, then on this side, when we integrate here, what we get, since we have du over u, we essentially have the natural log of mu. And sorry, I have to apologize. Sometimes I see this and I say u, and sometimes I say mu, but really I mean mu. So what we get then is if we choose k equal to 0, then the integral of p of t dt is equal to the natural log of mu of t, which means mu of t is equal to e raised to the integral p of t dt, and this is exactly how we get our integrating factor. And the key, again, is when you take the derivative of mu of t y of t, you want it to equal to this function here on the left, your original differential equation multiplied by mu, and that will give you, when you integrate both sides, you'll fall out with mu of t y of t is equal to the integral of the right-hand side. And then dividing both sides by y of t, this is the form of your solutions. And sometimes it's integrable in terms of elementary functions, but often it is not, and often you just use this as your general solution, where s is a variable of integration, and t naught is a convenient lower limit of integration. And I have the general solution here, and the note that if g of t is more complicated, you might leave your solution in this form. So let's do another example. Let's solve t y of t plus 2y of t is equal to 4t squared, and the initial value y1 is equal to 2. The first thing I'm going to do, so I have the correct p of t, is put our equation into the form dy dt plus p of t y of t equals g of t, which requires dividing the entire equation by t, so that I get y prime of t plus 2 over t, y of t equals 4t. Now I can calculate my integrating factor as the exponent raised to, or e raised to the integral of my p of t, which is 2 over t dt. And what that will give me is e to the 2 natural log of t, which is equal to t squared. Now that I have my integrating factor, I'm going to multiply my entire differential equation by my integrating factor, and I'll get t squared y prime of t plus 2t y of t is equal to 4t cubed. And again, I'm going to note that my integrating factor times y of t, when I take the derivative of that, I'm going to get 2t y of t plus t squared y prime of t, which is exactly what I have here, and just in different order. So I can integrate both sides of this equation with respect to t. This part here, when I integrate, I'm just going to come out with my integrating factor times y of t, t squared times y of t. This side, when I integrate, I'm going to get t to the 4th plus c, which means dividing both sides by t squared, that y of t is equal to t squared plus c over t squared, and this is my general solution. To get my particular solution for the initial value problem, I plug in y of 1 is equal to 2. In other words, t equals 1, y equals 2. So here I have y of 1. Plugging in for t equals 1, I get 1 squared, which is 1, plus c over t squared, which is just c, is equal to, and then y of 1 is equal to 2, which tells me that c is equal to 1, and my initial value problem solution is y of t is equal to t squared plus 1/2 t squared. So again, here is my general solution. Here's my solution to the initial value problem. And here are graphs of the solution. This next example is a case here where g of t is a more complicated function. So I have 2 y prime of t plus t y of 2 is equal to 2. That doesn't seem particularly complicated, but let's see where we go. And y of 0 is equal to 1. We are going to put this into dy dt plus p of t, y of t equals g of t form. So we divide everything by 2 and we get y prime plus 1/2 ty is equal to 1. We're going to find our integrating factor, which is e raised to the integral. Here we have p of t is 1/2 t dt. So that's e to the 1/4 t squared, which is e to the t squared over 4. I'm going to multiply my original differential equation, or my transformed differential equation by my mu, and I get mu t to the t squared over 4 times y prime of t plus 1/2 t y of t times e to the t squared over 4, and that's equal to e t squared over 4. I'm going to integrate both sides, noting that my integrating factor times y of t is equal to exactly what's in this integral. So I get mu times y of t is equal to the integral of e to the t squared over 4. And this is something that we're going to leave in this form, in this integral form. So I'm going to divide both sides of the equation by e t squared over 4, and I get y of t is equal to e to the minus t squared over 4 times the integral 0 to t e to the s squared over 4 ds plus c e to the minus t squared over 4. Remember, we switched to s just so we have this variable of integration. And this is our general solution. For our initial value, I have t equals 0, y equals 1. So here I have, plugging in for t equals 0, I have e to the 0, integral from 0 to 0, e to the s squared over 4 ds, plus c times e to the 0. And that all equals to 1. So this part here, since I'm integrating from 0 to 0, I'm going to get 0 plus c equals 1, which gives me c equals 1. So my initial value problem solution is y of t equals e to the minus t squared over 4, integral from 0 to t, e to the s squared over 4 ds plus e to the minus t squared over 4. So this is where we would leave this in integral form. So that is the material for this video. So again, we looked at first order linear differential equations. What makes a differential equation first order? That means the highest order derivative is 1. So there's no second order derivatives, no third order derivatives. It's just dy dt as well as y. It's linear when the variable y appears by itself. In other words, there's no y raised to the nth power like y to the third or sine of y or e or some other number raised to the y. So in general, first order linear first order differential equations have this form: dy dt plus p of t times y of t equals g of t. So if you can get your equation in this form, it's a first order linear differential equations, and we looked at two possible ways we could solve this. The easy way, or hopefully your equation will allow you to do direct integration, gather all the y terms on one side and then integrate. But sometimes this integration will give you problems, in which case we would use the method of integrating factors by Leibniz, where we multiply the entire equation by this integrating factor mu of t, which is equal to e raised to the integral of p of t. P of t is this function of t in front of y, dt. We integrate it all. We note that our integrating factor was chosen specifically because the derivative of mu of t, y of t is equal to, by the product rule, mu prime of t, y of t plus mu of t, y prime of t, which means our integral, when we do our integral of our differential equation, it falls out to be mu of t, y of t. And we have these examples that we had covered in our video. So that's it for this video. Thank you for watching.